Hello everyone, welcome back. Now we are going to be looking at solutions to the problems from section 8.2. First up, we have a triangle given and we are asked to solve the triangle. This always means find all of the angles and all of the sides. Now notice we are given two angles, this 100-degree angle and this 60-degree angle, which means the missing angle can be found quite directly by adding up the angles of the triangle and setting that equal to 180 degrees because we are in degrees. Subtracting 160 from both sides gives us that the missing angle A must be 20 degrees. So we'll go ahead and mark that in there, call that 20 degrees. Okay. Now, however, we're looking for some side lengths, but notice we are not in a right triangle. Okay, there is no 90-degree angle in this triangle, so we can't just use straightforward sines, cosines of angles. What we have to do is we have to rely on something called the law of sines. Okay, so the law of sines states that in any triangle, whether it's a right triangle or not, the sine of an angle divided by the side across from it is the same regardless of which angle and side pair you pick. Sometimes this will be given as the side length divided by the sine of the angle. And that's just reciprocating what's written above. It doesn't really matter which one you use, as long as you're consistent, whether you're putting angles in the numerator versus side lengths in the denominator or vice versa. Be consistent and it won't really make a difference. Okay, I tend to use this one where you have the sines up in the numerator. So what we're going to do is, since we know all of the angles, we can go ahead and put those in for the angles A, B, and C. Just remember that by default, angle capital B is taken to be the angle across from the side labeled B. So angle A was 20 degrees, and this will be divided by the unknown side length A. This is equal to the sine of capital B. That is the angle across from the side labeled with lowercase b. So if this is lowercase b, the angle across from that is 60 degrees, so we can go ahead and put that in. So this is the sine of 60 degrees over the side length labeled as b, is equal to the sine of our third angle, 100 degrees, divided by the length across from it, and that's just given as 8. Okay, across from the 100-degree angle is just a side length of 8. It's not actually unknown. So now what we do is we identify if all three of these are equal, then any two of them I pick must be equal to one another. So pick two of them where there's only one unknown. For example, if I pick these last two, I can say the sine of 60 degrees divided by b is equal to the sine of 100 degrees divided by 8. And now I can cross multiply. 8 times the sine of 60 degrees is equal to b times the sine of 100 degrees. Solve this for b by dividing by the sine of 100 degrees and get b is equal to 8 times the sine of 60 degrees divided by the sine of 100 degrees. I would point out that 60 degrees is an angle that we simply know the sine of. We can check a reference triangle, or you can just work through the 30, 60, 90 triangle yourself to figure out that the sine of 60 degrees is the square root of 3 divided by 2. Okay, I'm going to cancel that 2 with that, and this is therefore just 4 root 3 over the sine of 100 degrees. Okay, so there is side length B. I'm going to go ahead and label it on this triangle. This is 4 root 3 over the sine of 100 degrees. And now the only thing we have left to find is side A. Okay. Now, again, we come back to the statement of the law of sines here on the left, and we ask which two of these can we select that only has one unknown in it. And notice that that middle term, the denominator of lowercase b, that's not really an unknown anymore. But still, lowercase b is 4 root 3 over the sine of 100 degrees. So rather than work with that, I'm just going to work with the first and third expression. They are equal to each other. And get that the sine of 20 degrees over the missing side length A is the sine of 100 degrees over the given side length 8. Cross multiply. 8 times the sine of 20 degrees is equal to A times the sine of 100 degrees. Divide by the sine of 100 degrees to get A is equal to 8 times the sine of 20 degrees divided by the sine of 100 degrees. Now, a somewhat common error is to do something like cross out the signs and say this is 8 times 20 over 100 and simplify from there. But sine is not a number. Sine is a function. The sine of 20 degrees over the sine of 100 degrees. You can't cancel the signs. You can't simplify the 20 with the 100 degrees in any kind of way. Sine of 20 degrees is just a number, and sine of 100 degrees is just a number. This is really not simplifiable. You could plug this into a calculator and get an approximation, but as always, I'm not terribly interested in doing that. So this is 8 times the sine of 20 degrees over the sine of 100 degrees. Of course, when you're checking your work with MyLab, it tends to ask you for a decimal approximation, in which case you would want to do that. Just make sure your calculator is in degrees mode for this problem, rather than radians. All right, moving on. Again, solve the triangle. We're given 2 angles and 1 side, just like last time. So we're going to find our missing angle first. So 100 degrees plus 40 degrees plus the only missing angle must equal 180 degrees. Subtracting 140 from each side, A must equal 40 degrees. So I'm going to go ahead and label that in there. At which point, observe that this triangle has 2 angles that are equal. In other words, this is an isosceles triangle, which means the 2 sides across from the angles must be equal. So since across from this 40-degree angle is a side of length 5, across from this 40-degree angle must be a side of length 5. So I can just go ahead and note right away that this side must be 5. We can, however, get that from the law of sines, which would say the sine of angle A divided by the side across from it will be equal to the sine of the 40-degree angle divided by the side across from that. But we've already noted that A is 40 degrees. So if I cross multiply, we get 5 times the sine of 40 degrees is equal to A times the sine of 40 degrees, and division by the sine of 40 degrees, which is not 0, so we can divide by it, just gives me right away that A is 5. Which really means the only missing bit here is the other side length C, and again, we're just going to use the law of sines. The sine of an angle, 40, divided by the length across from it, now across from a 40-degree angle is 5, must be equal to the sine of 100 degrees divided by the only thing missing, which is the side length C. Cross multiply, and then divide by the sine of 40 degrees. And you're done. And again, there's really no simplification to be done here. So we've solved for the last missing bit in this triangle. We got A is 40 degrees, we got lowercase a is 5, and lowercase c is 5 times the sine of 100 degrees divided by the sine of 40 degrees. All right, moving on. Now notice that we're not given a picture. This is pretty common for exam problems just because it avoids us putting pictures in our exams, which takes work, and we're pretty lazy about such things. But that's fine. I'm just going to draw a triangle. I label the angles however I want. Just remember that sides go across from their respective angles. And now we just have to come in and note that B was given to be 70 degrees. So this is going to be 70 degrees, and angle C is 50 degrees. So I'm going to come back and mark those. And lowercase b is of length 8. And again, we're given 2 angles in a triangle, which means finding the third angle is just a matter of adding up all 3 angles of the triangle and setting that equal to 180 degrees. Subtracting 120 from both sides gives us A is 60 degrees. So I'm going to come back and put that in that corner. There it is. Notice I made no attempt to draw this triangle to scale. Okay, it looks like I drew an equilateral triangle. It's definitely not. Since I really had no idea what the various lengths were going to be when I started, I just presumed, you know what, my drawing's not going to look accurate, but it's a triangle at least. And now that we have all of the angles and we have one side, we can go ahead and use the law of sines. So I'd say, for example, the sine of 70 degrees divided by 8. I know I want to use the pair of this angle with this side because there's no unknown there. And I can set it either equal to the sine of 50 degrees over C or the sine of 60 degrees over A. And you know what? I'm going to do both because I do need to solve for A. But at the same time, I'm going to also need to eventually solve for C. So let's just do both of these at once. Okay, cross multiply. Notice that the sine of 60 degrees, as we saw in an earlier problem, is root 3 over 2. If I multiply that by 8, I get 4 root 3. Okay, and now on both, we're going to divide by the sine of 70 degrees, because that will isolate the unknown length, and we'll get a is equal to 4 root 3 over the sine of 70 degrees, and c is equal to 8 times the sine of 50 degrees over the sine of 70 degrees. And that's really all there is to it. We now have all of the sides, A, B, and C, and we have all of the angles. So this one's done. All right, this looks very similar to the previous problem in that we are given some information, but we're not given a picture. So let's go ahead and draw a picture. Okay, so the one angle we're given, I'll put in the bottom left, that's 30 degrees. Since that's capital A, across from it needs to go side length A. If I call this B, I'll call that 9, which means this is B, and our unknown side and unknown angle are going to be C and C respectively. So if I'm going to use the law of sines, there's really only one pairing that will only involve one unknown. Since I don't know the angle C and I also don't know the side length C, we're going to leave that alone for the time being. Okay, but the sine of 30 degrees over 10 must be equal to the sine of B over 9. Okay, and now I need to solve this for the angle B. Just multiply both sides by 9 to get 9 times the sine of 30 degrees over 10 must equal the sine of B. I would point out that the sine of 30 degrees is exactly 1/2, so this becomes 9 over 20 is equal to the sine of B. Okay, so this tells me that B is arcsine of 9/20, but now I need to be pretty careful, okay? Because if I'm looking in the unit circle, okay, 9/20 is very close to 1/2, so it's about here, and since I'm looking at a sine of something being 9/20, I'm looking at a y coordinate. Notice that there are two possible angles, okay? There's this angle, or there's this one all the way over here, which I'll draw in a different color for clarity, okay? This angle all the way over here also has a sine of 9 over 20. And since we're not restricted to being in a right triangle, I could have angles larger than 90 degrees in a triangle. Arcsine only gives me the one in the first quadrant, okay? So this angle right here, this is arcsine of 9/20. Based on some symmetry arguments, the green angle is pi minus the arcsine of 9/20 in radians, or 180 degrees minus the arcsine of 9/20 if you're in degrees mode. Okay, so remember that arcsine is going to be a little tricky to work with. It only gives you answers in quadrants 1 or 4 on the right half of the circle. If there's another solution on the left half of the circle, you need to figure out what that is based on some symmetry arguments. Okay, now for clarity's sake, I'm just going to go ahead and compute arcsine of 9/20. And since one angle was given in degrees, I'm going to make sure that I also do that one in degrees. So I'm just using another tab just to compute arcsine of 9/20 in degrees. Okay, arcsine of 9/20 is automatically, by default, the calculator that I use uses radians. So to convert from radians to degrees, I'm going to multiply it by 180 and divide by pi for a net result of 26.74 degrees. Sorry, I should code that in red because that is our first quadrant solution. And if 26.74 is the arcsine of 9/20, then the other possibility is 180 minus that, which is going to be sorry, not 173, but 153.26. Okay, so there are two angles in the circle that have a sine equal to 9/20, okay, 26.74 degrees or 153.26 degrees. So there are possibly two values of b that could be used to complete this circle. Okay. So coming all the way back to the diagram that we started with, the angle b in the bottom right has two possible values. The question becomes, are they both really possible? Just from the law of sines and getting a 9/20 out, we got these two possible values, 26.74 or 153.26. Okay. Are they both actually possible? No, because as soon as we have two angles in a triangle, the first thing we would do is say, well, great, let's find the third. And if we attempt to find the third angle, two different things could happen. So first, if I used capital B to be 26.74 degrees, then the sum of the three angles has to equal 180 degrees. We know A is 30 degrees. We just said B is 26.74 degrees. C is the unknown. If I just subtract 30 and subtract 26.74 from both sides, okay, we get 180 minus 30 minus 26.74. So that's 150 minus 26.74. So that's 123.26 degrees. Great. On the other hand, what if I said that B was 153.26 degrees? I'd do the same thing. I'd say the sum of the three angles must equal 180 degrees. Now A is 30, and B, I just said, what if that's 153.26? Well, now we're going to get a problem, because notice that 30 plus 153 point something is bigger than 180. So this is 183.26 degrees. So what would C have to be? It would have to be negative 3.26 degrees, and I can't in an actual triangle have a negative angle. In the circle-based approach, negative angles are fine, but in triangles you can't have negative angles, so this doesn't make any sense. Which means I can't actually have B be larger than 150 degrees. So there was really only one solution. B is 26.74 degrees, in which case C is 123.26 degrees. So I'm going to come back here and I'm going to make my triangle a little bit bigger because those are going to take some more space to write. So B has to be, its only possible choice is 26.74 degrees, which means C must be 123.26 degrees. And now the only missing thing is side length C, and I'm going to find that using the law of sines. Okay. So just to rehash what we've done so far, we started off by saying, well, what's the angle across from side B? What's angle B? And the law of sines told us that the sine of that angle had to be 9/20, but there are actually two possible angles that have a sine of 9/20, 26.74 degrees and 153.26 degrees. But because this angle was already 30 degrees, this angle couldn't have been 153 degrees. So the only legitimate choice was 26.74, which made this 123.26 degrees. And now we can come back and say, great, the sine of 123.26 degrees divided by the only missing thing is going to be the sine of 30 degrees over 10. So cross multiply, 10 times the sine of 123.26 equals C times the sine of 30 degrees. Remember, the sine of 30 degrees is 1/2. Excuse me, multiply the 2 to the other side and get 20 times the sine of 123.26 degrees is equal to the one missing side length C. And now we've completed the triangle. There was only one possible completion. Geometrically, what's happened here, and I'm going to erase everything now. Now I'm going to try to actually make things to scale. So I have a 30-degree angle and a side of length 9. I don't know how long this side is, And I know I have a side of length 10 that I need to attach to this here, but I don't know at what angle. Now, I can do it like this, just slightly longer than that. And you can see based on this picture, since this length and this length are pretty close to one another, these two angles should be pretty close to one another, and this angle is quite large, and that's the triangle we solved for. But imagine that this angle in the top has not been fixed. Okay, so this this side of length 10 is sort of allowed to swing around like it's on a hinge, because I don't really know what this angle is yet, and I don't know how long this side is, so there's some freedom here. Now, if I tried swinging it all the way around, because this was bigger than that, it would actually miss it and come back over here. So if I wanted to complete this side length and this side length, I would no longer have this angle of 30, I'd have an angle back here of 150. Okay. If, however, this 10 was shorter, so if I put like a 9 here, a 30 degrees, and I put something like an 8, well, then I could complete it here, but I could also swing it around on its hinge and make this triangle, and then there would have been 2 possible completions. Okay, anyway, let's keep going. All right, once again, we're given 2 side lengths and a single angle, so this is going to look pretty similar. So if I call this 80 degrees, then this had better be 1. I'll call this 10, which makes this angle B, angle C, side length C. All right, then I come back around and I say, hooray, the sine of 80 degrees divided by the side across from it, 1, must be equal to the sine of B divided by the side across from it, which is 10. I cross multiply and I can ignore division by 1. So the sine of B must be equal to 10 times the sine of 80 degrees. Hooray. Now the sine of 80 degrees is pretty big. Okay, remember the sine of 90 degrees is 1. So if I go ahead and I compute, what is 10 times the sine of 80 degrees? That's about 9.85. So the sine of B is approximately 9.85. And then B is the arc sine of 9.85. And we punch that into a calculator and it says error. Okay, and back in the before times when we had in-person classes, at this point a lot of students raise their hand and say something's wrong with my calculator. Nope, there is nothing wrong with your calculator. You never should have taken the arc sine of 9.85. Okay. Remember, the sine of an angle must be between 1 and -1. So how can I have an angle whose sine is 9 point something? You simply can't. There is no solution here. Okay, you can't have the sine or cosine of an angle larger than 1. The angle can be larger than 1. I mean, the sine of it can't be bigger than 1. And in this case, we have the sine of an angle is approximately 9.85, definitely bigger than 1. This is a problem. There is no triangle at all. Okay, this cannot be solved. All right, moving along. All right, we've got a figure on the right. Okay, to find the length of the span of a proposed ski lift from A to B, a surveyor measures a certain angle, DAB, at 25 degrees, that's marked in the figure, then walks 1,600 feet to C. Okay, so I'm going to go ahead and label this in the diagram. This is 1,600 feet. Okay, and then measures an angle of 15 degrees. What's the distance from A to B? Okay. So if I draw this triangle a bit bigger, we've got this angle is 15 degrees and this length is 1,600 feet, sorry. Then this angle here is 25 degrees, which means this angle here is 180 minus 25, aka 155 degrees. So inside that triangle, I've got the supplementary angle of 155. And observe that I now have a triangle with 2 angles given inside. So this third angle up top, I can quickly find by saying 155 plus 15 degrees plus the unknown. Since it's across from a side I've labeled as a capital L, let's just call that angle lowercase l. That has to equal 180 degrees. 155 plus 15 is 170, which means lowercase l is 10 degrees. So I'm going to go ahead and label that in here. And now this distance from A to B, this is our unknown. This is what we are trying to measure. But since we've got this angle and this angle across from our unknown side, we just set up the law of sines. The sine of 15 degrees divided by our unknown distance must be equal to the sine of 10 degrees divided by the length across from it, which was 1600. Cross multiply. 1600 times the sine of 15 degrees is our unknown length times the sine of 10 degrees. Divide by the sine of 10 degrees. To get our unknown distance is 1600 times the sine of 15 degrees divided by the sine of 10 degrees. And we could punch that into a calculator or computer to get an estimate, but I don't particularly care to do that. And there's our distance from A to B. That's the distance of the ski lift. All right. Another diagram picture. We've got an airplane that's at the point Z, spotted by two observers at X and Y, who happen to know that they are 1,815 feet apart. So this entire distance is 1,850. Okay. Each observer takes a sighting of angle of elevation. The angle at A, that's corresponding to our observer X, is 25 degrees. And the angle at B is 30 degrees. How high is the airplane? Now what we don't know is where in between X and Y the plane is. It's somewhere in between them at a particular height, but we don't know this distance compared to this one. We just know that those two distances will sum to 1,850 because that's the distance between our observer. Okay. So there are a few ways we can go about this problem. I'm actually going to ignore, for the moment, this height. I'm going to complete the large triangle. And in the large triangle, I've got 25 degrees, 30 degrees, and 1,850 feet. Now I know that the angles of this large triangle have to add up to 180. So if I call this C, let's just say, we know that C plus 25 degrees plus 30 degrees is going to have to equal 180. Subtracting 55 degrees from both sides gives me that C must be equal to 125 degrees. Okay, so let's go ahead and put that in there. All right. As long as we're at it, we can find some missing side lengths. Okay, so if I'll call this side length A and I'll call this, I should call this side length B because this angle was already marked as capital B on the lower right, and I'll call this side length A. Setting up the law of sines, we get that the sine of 125 degrees over 1,850 is the sine of 25 degrees over A. Okay, cross multiply. A times the sine of 125 degrees is equal to 1,850 times the sine of 25 degrees. Divide by sine of 125 degrees. A is 1,850 times the sine of 25 degrees over the sine of 125 degrees. And because I happen to know later in the problem we're going to need to do further computations with this, I am going to go ahead and get a 2 decimal point approximation for this. So 1,850 times the sine of 25 degrees divided by the sine of 125 degrees. And I've got 954.45. Okay, so I'm going to go ahead and label that as this distance here. Okay, that was my lowercase a. It was the right side of the triangle. So I'm going to go ahead and just put it in the top diagram. This is about 954.45. And now we're going to go ahead and do a similar work trying to solve for side length B, the left of the triangle. I'm still going to use angle C and side C because they don't have wonky measurements in them. They're not decimal approximations. And I'd rather not compound any rounding errors. So the sine of C over C is equal to the sine of angle B, which is 30 degrees, over side length B. Cross multiply. B times the sine of 125 degrees equals 1850 times the sine of 30 degrees. As we've used a few times, the sine of 30 degrees is 1/2. So b times the sine of 125 degrees is simply equal to 1850 over 2, which is equal to 925. Dividing by the sine of 125 degrees, b is 925 divided by the sine of 125 degrees, and I'm going to go ahead and round that off to 2 decimal points. 925 divided by the sine of 125 degrees. 1129.22. Okay, and I'm going to go ahead and label that as this side over here, 1129.22. Okay, now we can finally turn our attention to trying to find the height, that missing bit in there. And to do that, there are a few options. So some people whose geometry is quite strong might remember there's something called Heron's formula, which if you know all 3 sides of a triangle, you can get its area. And I do know all 3 sides of this triangle, which means I could use Heron's formula to compute its area. And if I know the area of the triangle, it's 1/2 1850 times h. So if I know the area, I could solve for h that way. That's kind of overkill, I happen to think. So instead, we're going to take a look at splitting the large triangle into the 2 smaller ones. So the triangle on the left versus the triangle on the right. Okay, now the triangle on the right has 30 degrees here and a right angle, and this is definitely 954.45. The triangle on the left has a 25 degrees and a right angle, and this is definitely 1129.22, more or less. We rounded to 2 decimal points, remember. Okay, now the unknown is h, which is the same opposite side here. So we can use either triangle we want, and we'll go more or less the same way. Which trigonometric ratio in the triangle on the left is going to use this angle, the hypotenuse of the triangle, and that height? Sine of 25 degrees. What about on the right triangle? This angle, this height, and this hypotenuse. Also sine. So either way, we're going to have a sine either of 25 degrees or of 30 degrees. And since the sine of 30 degrees is exactly 1/2, I'm going to use that. So the sine of 30 degrees is opposite over hypotenuse, which is our missing height over 954.45. Okay, the sine of 30 is exactly 1/2, so we have 1/2 is equal to h over 954.45, or h is 954.45 over 2, just by multiplying both sides by 954.45. Pardon me. And if I just round that off, 954.45 over 2, we get 477.23. So there is the height of the airplane, rounded off to 2 decimal points. Okay, to get the height of this triangle, we solved for the outer triangle overall. As long as we were doing it, we found all of the sides. However, now that we've gotten to the end of the problem, observe that we really only needed this right triangle here. So as soon as we had this 954.45, we could have stopped. We didn't need to find this other side length of 1129.22. But hey, extra practice is never a bad thing.